This is Mark Schneider from Grinnell College, and I'm going to talk a little bit about rotational motion, and we're going to look at some things rolling down an inclined plane as a way of getting at this concept of rotational motion, or as it's sometimes called, rigid body motion. You've seen these different objects rolling down this inclined plane, and you should see that some of them roll faster than others. I've done this in comparison with a cart and a solid disc and a hoop, and then also this mysterious cylinder, and we're going to talk more about why it seems to do something very odd. As we analyze this, the first thing to do is let's imagine just a block that's sitting at rest on an inclined plane. So there's enough frictional force that it's not sliding down this. Here it's really easy to analyze. That is that there are two forces acting on this. One is the force of gravity that's downward, and the plane, since the object is not moving at all, must exactly balance that in the opposite direction. Now conventionally what we do with this force that the plane is exerting is we break that into two components. One, the force of friction, and the other, the normal force. The normal force is simply the force that's perpendicular to the plane. And since the block neither leaps up off of this plane nor crashes through it, we know that the forces perpendicular to that plane must balance exactly at all times. So this means it becomes a one-dimensional problem. So all we need to consider are the forces that are along the plane. So we're going to go ahead and do that. That tells us now that we should do exactly the same thing for the force of gravity and look simply at the component of that along the plane. But when we start talking about things that are actually rotating, we're going to now have the added complication of a torque being applied to the rotating object. So that is as we see here, we're going to find that force of friction that is exerted right at the contact point and the component of the gravity force along the plane that is acting on the center of the object. So only the force of friction there is exerting a torque. This now gives us two equations of motion. One is the linear motion, F equals ma, and the other is the angular motion. The corresponding equation is torque is equal to I alpha, where I is the moment of inertia and alpha is the angular acceleration. Just to remind you, the motion, the displacement along of the surface of a rotating object, this delta S, is proportional to the angular rotation delta theta by the radius of the object, the distance away from the center of rotation. And in fact, it's this proportionality that actually defines the radian for us, so that we have this nice simple relationship of distance being related to angle. And we have the corresponding derivatives of this that give us the velocity and acceleration related to the corresponding angular velocity and angular acceleration. So let's now come back to our rolling cylinder or hoop or disc and look at this one-dimensional problem, and we have written out now our two equations of motion that we're going to now need to solve simultaneously. And there are those two equations. I'm going to copy them again onto a second page here. And let's just take note that if there is no force of friction, we have a very simple result. That is, mg sine theta is equal to ma, which tells us that the acceleration is just equal to g sine theta. And this is true if a block is sliding frictionlessly down the inclined plane, or equivalently if I have a cart that has some very tiny effectively massless wheels on there that are allowing it to go down frictionlessly. So to solve these equations simultaneously, we're going to solve for the force of friction and then substitute that into the other expression. So solving for the force of friction in the linear motion equation and putting that into the angular equation. That way we can eliminate the force of friction, one of our unknowns that we don't really care about, and solve for the acceleration, which is what we really want to know. So once we've done that, there's a little bit of algebra to rearrange some things, and then we're left with an expression that has the moment of inertia. And the moment of inertia, this I, in the hoop case where the mass is all on the outside edge, is simply equal to mr squared. So I can substitute that and find that the acceleration that I get is simply half of what it would be for the case in which it were was just a block sliding down. In the case of the disk, here the moment of inertia is mr squared over 2. We evaluate this by actually doing an integral of mr squared over the disk, and we find that that comes out with that factor of 2 difference. So this now gives us an acceleration that is 2/3 of the acceleration that we would have had in the case of the frictionlessly sliding block. So now we see that we have exactly the relationships that we saw qualitatively in the video of the things rolling down the inclined plane. That is that we have the fastest being the cart, the next fastest being the disk, and the slowest being the one that has the largest moment of inertia for its mass, that is the hoop. Finally, let's come back to this case of that mysterious tube that rolled only part way down. This one turns out inside it's half filled with sand. And before I put this on the board, I made sure that all the sand was at one end by tilting it up vertically, and that allows it to roll part way, but as it rolls down, the sand resettles halfway through it and causes it to stop. And you might think, well, that's just a silly trick, but there's an important element in this, and that is that in there, this is not a rigid body. Inside the cylinder, pieces are allowed to move around. Anytime we have something of that character, the dynamics become much more complicated than they do for rigid bodies, for objects in which all the pieces stay in their same relative positions. So it's a caution to you. Make sure that when you're solving some of these problems that you are looking at things in which indeed the relative spacing, or equivalently the moment of inertia, stays constant.